Alright, hi Year 11s, this is Mr. Lim here again, and this is our final video on aqueous solutions on parts per million and density. So let's get started. Alright, okay, so we're going to go do these things here. We're going to do a couple of calculations and a couple of formulas. So let's get going. Okay, so the first one is parts per million. So parts per million is ppm. Okay, parts per million, that makes sense. It's used to describe things which are in very, very small concentrations because it is effectively the solute mass in milligrams, which is a very small unit, over the solution mass in kilograms. Okay, so 1 milligram is actually 1/1,000,000th of a kilogram. That's why it's called parts per million. Okay, so you have to remember this equation. It's also on the data sheet, but the idea is that it's solute over solution mass, and this is what we've actually been doing a lot in terms of concentration. We've always been doing some sort of amount over some sort of total or total volume or total solution mass or something like that. So it's something we're just going to continue on. That's what concentration is. Okay, so let's go look at some examples. Okay, so the first example, if there is 0.26 grams of lead in 30 kilograms of water, determine the concentration in parts per million. Okay, so first of all, remember parts per million, we need to get the solute in milligrams and the solvent or the solution in kilograms. So we need to work out the mass of lead, which we know is 0.26 grams, but what's that in milligrams? Well, you times that by 1,000 because there is 1,000 milligrams in a gram, and you get 260 milligrams. Okay, so effectively you should remember that grams to milligrams is times 1,000. Okay, so then we can solve for the parts per million. So parts per million of lead is going to be 260 over what's the mass of the solution in kilograms? It's 30, which happens to be 8.67 or 8.6 recurring parts per million. Okay, so nice and straightforward. It's going to be a lot of converting between different masses and things like that. All right, so let's move on to the next one. Determine the concentration in parts per million if 2.1 grams of gold is collected from 25 tons of seawater. Okay, so again, we need to work out the masses of the things in the appropriate unit. So if the mass of gold is 2.1 grams, okay, we need to convert that into milligrams. So that is 2,100 milligrams. Okay, 2.1 times 1,000, that's 2,100 milligrams. Okay, we need to work out the mass of the solution, which is, well, let's have a look. It's 25 tons. A ton, 1 ton equals 1,000 kilograms. So 25 tons is 25,000 kilograms. Okay, and then you can do parts per million of the gold in the, make sure you nice, neat handwriting. Gold in the thingy is going to be 2,110 over 2,5000, which happens to be 0.084 parts per million. Parts per million, which is the unit. Okay, let's move on. So determine the mass of osmium in 21.2 tons of ore if there's a concentration of 46 parts per million in the ore. So now we're given the parts per million, we're given the mass of the total. Now we have to work out the mass of the individual part. All right, so let's convert everything into the appropriate units. So the mass of the ore is 21.2 tons. Okay, which equals to 21,200 kilograms. Okay, so we're just converting it into the right unit. Mass of then osmium will be equal to parts per million times the mass of the ore. Okay, this is just a rearrangement of ppm equals mass osmium over mass ore. Okay, rearrange that equation and you get parts per million times mass of the ore. So that equals then what? 46 parts per million times 21,200, which happens to be what? 975,200. And what's the unit going to be? It's in milligrams, okay? Because that's what the unit for the mass on the top of the parts per million equation is going to be. We have to keep the right units. which happens to be 975.2 grams. Okay, right. Then finally, determine the number of moles of carbon dioxide in 40 kilograms of air if there's a concentration of 400 parts per million. Okay, so let's have a look at that one there. Again, we're looking at the mass of CO2, which will be equal to, okay, but parts per million, times the mass of the, where was my pen gone? The mass of the ore, right? So that makes that parts per million 400 times 40, okay, which is equal to what number? 16,000. Okay, now that seems like a large number, but remember, what's the unit going to be in? It's going to be in milligrams, so that's going to be divided by 1,000. So milligrams to grams is divided by 1,000, right? So it's going to be 16 grams. And then this wasn't the end of the question because we want the number of moles of carbon. So the number of moles of carbon, we can do that. Okay, so 16 over 44.01, which will be equal to some value like 0.364 moles. Okay, all right, let's move on. The next one. Okay, so now we're going to find out the mass of the solution when given the parts per million and the mass of the solute. Okay, so determine the mass of seawater that would be required to collect 2.4 kilograms of gold if the concentration is 0.0003 parts per million. Okay, so we need to convert stuff into the right unit. So the mass of the gold, it's 2.4 kilograms, right? But we need it in milligrams because that's going to be the thing that we're searching for. That's the part within the million. Okay, so that's 2,400 grams, but then that's 2,400,000 milligrams. That's how many milligrams we're looking for, 2.4 kilograms. Okay. Then we rearrange the equation. The mass of the seawater will be equal to, right, what? The mass of the gold over the parts per million. Okay, that's the rearrangement of the ppm equation. Okay, so therefore it's 2.4 million over 0.0003, and this number gets quite large. 8 times 10 to the 9. And what's the unit? This is in kilograms, okay? So it's a lot. That's a lot just to get 2.4 kilograms of gold, okay? Determine the minimum mass of water in a lake which holds 283 grams of lead if the lead concentration is if the lake has a lead concentration of 9.4 plus or minus 0.05 parts per million. Okay, so again, we're going to go convert things into the right unit. So the mass of lead, we know it's 283 grams, which is in milligrams, 283,000. Okay, that's the lead inside the lake. So that's the mass of the individual solute rather than the solution, right? The mixture. So to get the minimum mass of water, we are going to assume the maximum concentration. Okay, the maximum concentration. So the maximum concentration would lead to the lowest amount of water that you would need to have that concentration. So if we are going with 9.4 plus or minus 0.05 parts per million, the parts per million of the lead max would be 9.45 parts per million. Okay, so then from there, the mass of the water that it's all dissolved in would be, again, mass of the part over the parts per million. Okay, so 283,000 over 9.45, which happens to be 29947. And what's the unit? Kilograms. Okay, so that is parts per million. You just have to be able to rearrange the parts per million equation, and it is in the data sheet, and you need to remember the specific units and how to convert from and to those units. Okay, let's have a go at the next bit. Density. So density is the mass per volume of a particular substance. Okay, mass per volume. Okay, it's kind of like concentration, but it's more about just how heavy something is for the volume that it is. All right, so that old joke about which one's heavier, a ton of feathers or a ton of bricks, okay, them both being the same mass, but they will have different densities and therefore they will have different volumes because their masses are the same, but their densities are different. Okay, so it's often used in concentration calculations to convert, and this is the key idea, is to convert between mass and volume. Okay, so changing between mass and volume, you need to have this density calculation, and the density calculation can be summarized as D for density, right? M over V. Okay, so that is the density, and you'll notice that it actually has the same equation as like concentrations, like grams per liter. It's got mass per thing, so grams per liter can also be a concentration, but it can also be a density. Okay, but the density would be of the whole solution, not just of the solute within the solution. All right, but any mass of any volume, and you have to be able to convert it from the various units. Okay, what I will say is that when you look at the question, you have to look at what the unit is and convert things to that unit, and then you'll be able to solve the answer. All right, so let's look at the first couple of examples. All right, so let's go convert these into the requested form. So 2.6 kilograms, so 2.6 kilograms per liter. If you think about 1 liter, that would be the same as saying it's 2,600 grams in that 1 liter. Okay, because what I've done is that, okay, to go from kilograms to grams, I've times it by 1,000. Then, if it's in 2,600 grams per liter, how much would there be in 1 mil? Remembering that there's 1,000 mils per liter, you would divide this by 1,000 to go to 2.6 grams per mil. Okay, so I guess the tricky thing is that recognizing whether you are changing the unit above or below the fraction. So you should recognize that this thing here is effectively a fraction. Okay, if you're changing the unit above the fraction, you have to do something different to when you change the unit below the fraction. So you've got to think about, okay, if I have 1 liter of this thing, how many, if I have 1 liter, I have 2.6 kilograms, which is the same as 2,600 grams. But if I have 1 liter of this thing, it's the same as saying, okay, I have 1,000 mils of this thing. And so therefore, to make it per mil, I have to divide it by 1,000 here. Okay, so it's a bit tricky, but we have to get through these unit conversions. So let's try the next one. 94 milligrams per mil, okay, into kilograms per liter. Okay, so the idea is that now if I go then, all right, that means that if there's only 94 milligrams in every mil, okay, 94 milligrams, I'm going to be dealing with the weight first, okay, but a milligram, how many grams is that, right? So then I want that to be 0.094 grams per mil, right? Which is effectively the same as doing 0.000094 kilograms per mil, okay? And then you can also then change that to, right? Now I've say, okay, that's how many kilograms in every mil. Now I need that into liters, so I have to times it by 1,000. And that will lead to 0.094 kilograms per liter, right? And if you look carefully that these two are the same, okay, so grams per mil and kilograms per liter will actually end up the same. And then you can see that in the last one as well. Grams per mil and kilograms per liter will be the same value, okay? But let's go do the last one, okay, because the last one has something a bit tricky. Okay, so it's grams per liter into kilograms per meters cubed, and a meter cubed is 1,000 liters. Okay, so let's go do that. So 28 grams per liter. Okay, effectively, let's convert that into kilograms. So we divide it by 1,000 to get the kilograms from grams. Okay, that's kilograms per liter. Then 1 liter, it's got that much per liter, 0.028 kilograms in 1 liter. 1 meter cubed is 1,000 of those. So I'm going to times that by 1,000. All right, times that by 1,000, and it goes back to kilograms per meters cubed, right? So grams per liter and kilograms per meter cubed are the same unit as well, okay? So there are a number of pairs like that, but the idea is that you need to think about how to convert between those things there, right? And if you need a bit of help, let me know and we'll go sort those out. But converting between densities is important. Let's go on, move on. So now we can convert between densities. We have to then start doing calculations of those densities. So let's have a look at the first one. Determine the density of a solution if 23.5 liters weighs 24.1 kilograms in grams per mil. So we're going to convert things. So volume of the solution is equal to 23.5 liters, which is the same as 2,350 mils. So we're converting liters to mils because that's what I'm trying to get to, grams per mil. All right, so that's the volume of the solution. The mass of the solution is equal to 24.1 kilograms, but I want that in grams, so that's 2410 grams, okay? Then I can do the density of the solution is equal to 2410 over 2350, which is equal to 1.03 grams per mil. Okay? All right, so that's that one there. Converting between stuff. So let's do the next one. Determine the density of solution if 2.2 meters cubed weighs 3.4 tons in kilograms per liter. Okay, so the volume of the solution, all right, is 2.2 meters cubed. If we remember that 1 meter cubed is equal to 1,000 liters, therefore it's 2,200 liters. Okay, I want the mass of the solution. I want that in kilograms, but I've currently got it in tons. So therefore I times that by 1,000 because there's 1,000 kilograms in every ton. So 3,400 kilograms. And then finally, the density of the solution will be the mass, 3,400, over volume, 2,200, and that'll be 1.55 kilograms per liter. Okay, so I've got to use the units here, otherwise it's not going to be right. Whatever unit I use, that's what I've got to put in the answer. Okay, and then whatever the answer asking for, that's the units I've got to turn it into. Let's move on. Okay, so determine the volume of methane gas required to pump in 60 kilograms of methane if the gas has a density of 0.075 grams per mil. Okay, so what's that one then? So the M of methane is equal to 60 kilograms. That's how much we need. However, I need that in grams, so that's 60,000 grams. Okay, because I need it in grams per mil. Because that's I have to match the unit inside the density value. Okay, so therefore, now that I've got that in grams, I can work out the volume of the methane by rearranging the density equation, right? So remember, D is equal to M over V, therefore V is equal to M on D, right? So mass, 60,000 over 0.75, okay? Over 0.75, which is 80,000 mils, which happens to also be 80 liters. Right, but remember, how do you know that this unit here is in mils? Because the density equation or the density value was given in mils, so this has to be in mils there. And then you convert it to liters if you want. Right, let's have a look at the next example. Determine the volume of seawater required to be pumped in every minute to process 400 kilograms of water every hour if the seawater has a density of 1.23 grams per mil. Okay, so again, mass of seawater, I got to go start converting these things. Now, this has a bit of a tricky thing in there because it's every minute and every hour. So I got to convert, so at least I got to write out what I'm solving. I'm solving for the mass of seawater in an hour, right? So 400 kilograms of seawater. So that's how much I'll need in an hour, 400 kilograms. I need that in grams. So that's 400,000 grams. Okay, why do I need it in grams? Because that's the unit that my density is in. Okay, So that's why I need to convert that into grams. Okay, so then I need to work out, okay, the volume of the seawater per hour, which is equal to, again, M on D, which is equal to 400,000 over 1.23, which happens to be 3.25 times 10 to the 5. What's that unit going to be in? That's going to be in mils, because that's the unit from the density. All right, so the unit that's going to match. Right, I need a bit more space. Okay, cool. And so therefore, now that we've got the volume of seawater in an hour, I can work out the volume of seawater in a minute, which will be, 1/60th of that. Volume of seawater divided by 60, okay, which happens to be 5.42 times 10 to the 3 mils, okay, and then if I want to convert that into liters, it's going to be 5.42 liters, okay. The idea is that times 10 to the 3 is effectively 1,000, so you get rid of that 1,000 because you're dividing it by 1,000 to get to liters, and that gives you 5.42. And this is liters per minute, but that already says it in the question. Okay, so next, okay, determine the mass of solution if 20 mils of the solution has a density of 1.4 grams per mil. Okay, so this is the mass of the solution, which will be equal to, now this is just a rearrangement of the D is equal to M over V, so M is equal to D times V, so density 1.4 times volume times 20. I don't even need to convert because it's already in the correct unit, okay? So it's 1.4 times 20, which is equal to 28. What's the unit that this is going to be? Well, it's a mass unit, and it has to match the unit in the density, so it's 28 grams, okay? Determine the mass of air pumped in every hour by a fan that has a density of 1.293 kilograms per meter cubed, and it moves 35 liters every minute. Okay, so let's have a look. So I have to convert these into the right unit. So this 35 liters, I need to convert it into meters cubed so that I can use the density equation. So the volume of air is equal to 35 liters, but that's actually also divided by 1,000, because remember there's 1,000 liters in every meter cubed, 0.035 meters cubed. Okay, so then the mass of the air, again, I'm rearranging that equation, so it's going to be D times V. So D, which is 1.293 times, in meters cubed, 0.035, which happens to be, 4.526 times 10 to the negative 2. What unit? Kilograms, because it's got to match the unit in the density, right? And then the mass of air in an hour, okay, because this one is every minute. This is every minute, okay, will be that value times it by 60. So for mass of air in a minute times 60, which will be equal to 2.7 kilograms, okay? So that is how you would answer those ones there, okay? Making sure that you're converting to the right unit, you're remembering what the units are. Let's move on. Last question, okay, a bit of a trickier one. So what volume of air in liters would be needed to provide 20 kilograms of hydrogen gas with sufficient nitrogen gas to produce ammonia gas if air is 70% nitrogen and has a density of 1.293 kilograms per meter cubed? So this one actually is a reaction, so therefore we have to have a balanced equation. So N2 plus H2 makes NH3. Okay, so I have to balance that equation, so that's going to be 3 and a 2. Okay, so now I've balanced that out equation. Okay, so how much nitrogen do I need? So nitrogen is what I'm looking for if I have 20 kilograms of hydrogen gas. So the idea is that this is my known, this is my unknown. So let's get started on my known. So N of the H2 gas will be equal to 20,000, because that's kilograms into grams. Remember this equation, m over m has to be in grams, okay? So it's 2.016, which is the molar mass of hydrogen gas, which is equal to 9.92 times 10 to the negative 3 moles. That's how much hydrogen I have. Then I can work out the number of moles of N2, which I require, okay, which will be equal to the number of moles of H2 times, what's the stoichiometric ratio? Unknown over known, okay? So therefore that one's going to equal 3.31 times 10 to the negative, or 10 to the 3, sorry. Sorry, that's not negative 3, that's to the 3, okay, mole, okay? So remember, you should be saving your numbers as well, but you know, I don't need to save it because I've already done it. Okay, so therefore, the next part is, okay, well, how heavy is that nitrogen going to be? Because I need to work out the mass of it, so if I can work out the volume of it from, because remember I'm using density to convert between mass to volume. Okay, so the mass of N2 will be equal to the number of moles of N2 times its molar mass, which happens to be 3.31 times 10 to the 3 times 28.02, which happens to be, what's that, 9.27 times 10 to the 4. What's the unit there? Grams, okay? Then I can work out the mass of the air. Now, in the original question, it says that the mass of the air, well, is 70% nitrogen. So therefore, the total air will be the mass of your nitrogen gas times 100 over 70. The idea is that the percentage of nitrogen is equal to the mass of nitrogen over the mass of air times 100. And so therefore, it's, you know, the part over total. And then if you rearrange that equation to get the mass of air, you would be doing it with the mass of nitrogen, right, times 100 over percentage nitrogen. Okay, that's the rearrangement of that equation. And that's what we did here. And so therefore that value is 1.32 times 10 to the 5 grams, okay, which is a lot. That's grams, but we need that in kilograms. Why do we need that in kilograms? Because our density value is in kilograms. So I have to convert that to there. So let me just move that. And so the mass of the, oops, I don't even need to do that. I don't need to rewrite that again. I just need to convert that. It'll be 1.32 times 10 to the 2 kilograms. Okay. Once I have that, I can say that, okay, then I need to convert between mass and volume. So the volume is equal to the mass over the density, right? I have a mass, 1.32 times 10 to the 2 kilograms, because that's the unit I have in my density, right? Over 1.293, which is equal to 1.02 times 10 to the 2, what unit? Meters cubed. Okay, but the answer asked me for it in liters. So therefore, there's 1,000 liters in every meter cubed. So it's 1.02 times 10 to the 5 liters. Okay, and that's it. Hopefully that was helpful so that you can see the examples. It's just about working out how to apply them into the various calculations. And that's all. Adios.